So the first step is that we want to think about what would be the best thing to do in general on the research frontier, because I was not doing the research. I was doing mainly write-up and pushing the conceptual clarification a lot further. Now I think it would be good to a bit more solve the bottleneck. So what's the bottleneck? So I think we need to reiterate what is the thing that we want to actually use this for. So we have to, so I think it would be good if we're assuming we're sort of in the world state graph setting, or I guess we could take a step further back to, we want to infer models of the world, but world state graphs still seem like we'll not fully explore them. This seems like a good direction to further go in. So what's the world state graph bottleneck? Yes, so okay, we could either like there were two main streams for the thing. Let's write it down. We want to focus on further exploring world state graphs and figure out what the bottleneck there is. Note that there were two approaches to generating the world state graph. Like the first one was about the coming up with hard-coded algorithms to detect structure. The second one, find a general structure detection algorithm. Okay. Well, we're not done with the waiting preamble, okay? Okay. So here's a good topic, I think, which is like super general structure detection. By which I mean something like, okay, here, what would be a concrete example of this? Yes, exactly. If we have repeating structure, then it would allow us to... Oh! Wait, so maybe this other algorithm that I was talking about with Thomas is actually pretty good. A good topic might be structure detection in general. For example, in a graph, simply detect repeating structure. That definitely works with any possible structure we could have. Yes, if we assume we could compute graph isomorphism efficiently, that actually probably would say we had. But detecting the repeating structure, like based on the structure is actually sort of the same, like it's the same sort of subgraph. That's just, that would detect the lattice, right? Well, okay. So is that the problem we want to think about? Well, like the idea is, I guess, something like Solomonov induction on graphs or something. Like, or how could we extract all the structure? Sort of like, in general, can we have a Solomonov induction like algorithm that would detect any structure? Well, or maybe actually not any structure, but sort of like, what kind of structure can we detect that is not so specific like lattice? Question, what are more such algorithms? So what do we, I guess we could think about, how do we use this repeating structure? So how do we use it? Right. Different ways in which structure can be useful. Create a small model describing a world state graph. enable certain algorithms to run fast, analogous to binary search. Okay, I'm not sure, are we still doing it? I guess, sort of. How can we use the structure? Well, there's two ways, right? Compression and representation, I guess. Without abstraction, though, note the two above are different from abstraction, but it seems structure could also somehow be useful in abstraction. And I have this Google document here. Right. Oh, that is a nice advantage. The setup we can definitely delete. In the preparation. It might be even that getting clarity on what is this abstraction thing is really useful. Potentially it's useful to clarify what abstraction is and how it relates to these different concepts of representation, compression, and so on, as this is central to what we are trying to do with world state graphs. Maybe something about general graph compression algorithms. Okay, yeah, something like parameterized compression, which is probably like something about the compression ontology. So compression ontology. Parameterized compression algorithms. Instead of finding exact repetitions, find a function and arguments to the function that would produce some objects you want to represent. Meaning you compressed these objects to needing to have the function and the arguments. That's pretty nice. Is this Solomonov induction? Right, sort of is not. This seems sort of very different from Solomonov induction, but I'm confused about how. Okay. So if you think about the very general structure detection algorithm, well, I'm not completely sure. So yeah, but kind of brute forcing. There is another thing of like, how is this different from Solomonov induction? We could also think about how a world state graph is different from Solomonov induction. It feels in Solomonov induction you're brute forcing what's the correct compression, whereas in Solomonov induction you, with the world state graph I mean. In a world state graph you instead have some local structure that you're analyzing and trying to describe. The robot arm experiment. Okay, so the robot arm experiment was about what? Right, they were about lattices. Oh, dang. L systems. Okay, this is like, how are L systems related to functions that generate graphs? I'm pretty sure you could have L systems describe the generation of a graph. Okay, so we could have something where, let's go here. So we could have a sort of, yes, so the function that generates the graph where we, so okay, let's just draw the graph again. So in Minecraft crafting, Minecraft block placement, 1D Minecraft block placement, we got this line graph where we branch off into different lattices here. And then, but we have this kind of branching off for every thingy. So like this would go over here. This would go over here. And now this would be looping. So we have a line graph, which we know how to describe, right? So is it also the same deltas? I think this is literally the same line graph. So let's say we have, this is the line graph. Now we could say something like how do we describe this graph? It's like line graph and then plus a line graph. So it's not enough to have the line graph. It is sort of, we need to specify now, like we need to say in this line graph the connections. Like basically we need to say like we have a line graph and then that is connected to another line graph, another line graph, another line graph, and so on. But all of these are a bit different because we are indicating, maybe with this edge, where the connection is. So we want to say something like, we need to say something like, here, this is sort of, I guess, a list, maybe? Is it a list? We could represent it as a list, for example, 1, 2, 3. So like the list is a natural number, contains a natural number, or it's a list of natural numbers, or integers, and it corresponds to where we traveled. How did we travel from the first graph to the second graph? Ah yeah, and the last entry, and is like the ordering in which we traveled. So like this would be having a thing which would be LG of like, for example, 1, 1. Okay, and this would be LG of the empty list. Yes, I think this is sort of a structure that could describe this graph. If we sort of have the appropriate definitions for what is LG. So LG is now the constructor, sort of. LG is the constructor takes this list and then sort of connects the vertices. I guess this number is sort of to index. Like if this is sort of, for example, when I'm saying something like this is 1 here, and this is 1 here, and this is 2 here, this is 2 here, something like that. So that we map all of these vertices to the corresponding vertex in the line graph. And we could do 2 steps and go from, we could go over here. No, actually we can't go over there, lol. Yes, this is actually unique. So LG takes a list of int and, is it the list of int? Unique list. Okay, unique list is like no repeating elements. Okay. So this definitely uses functions, the graph generating functions, right? Okay. Right, this is still infinitely large. I mean, the only thing we did is compress the lattice graph, sort of. Instead of writing out the, well, I guess we sort of also linked stuff between the structure. Right, so we described the lattice and the relation between the lattices. Couldn't we just say something like LG0 LG0 contains all for all natural numbers, a thing. So I think we could say something like, what is the structure around something in the original vertex? So then we would have like V, which let's say it's a number, integer or something. Then we would say like, okay, V maps to LG V, right? That makes sense. And then if you want to expand, well, if you want to expand LGV, we could just expand it into some letters, so like expand it a bit because we know what the definition is of LGV, so we could like lazily expand it. But let's imagine we could expand it at all if it's sort of finite or something. Or like makes more sense to expand it lazily. Like maybe expand it sort of around some vertex. If we could do that with this, then this would be pretty good. Because then we could be like, yes, just expand this. Now we get, well, actually you can't do that. Or like you can do this, but there's a problem. The problem is that you definitely would need to keep track of that this is LGV. We are in LGV right now. We need to know that, such that we can say that how to expand the V vertex in here, like with a certain label. Because that is not expanding into another lattice. That's the important thing. And I guess we're also mapping backwards potentially if this is a bidirectional edge. But other than that, right, that is the thing. We want to be like, so we want to generate a certain vertex in this graph. So we generate that vertex. And together with knowing in what graph we are, like that we're in LGV, we can now expand this graph further. We can predict what's happened if I would go down. Because if I got sort of like expand this, you can imagine I expand like I have V, and then I have here I have like V2, V3. Maybe it's like this. And here we also go sort of in the lattice. And then here, if you go down again, you could predict sort of, let's say this is 1, 2, 1 bar. And then this would be LG V1, V2, which we could then again unroll, sort of, is the idea. You just need to keep track of that. This is actually LGV. Okay. Then we can expand this. Okay, the thing that we didn't talk about yet is how to construct these arguments, but sort of it's pretty simple, right? It's just if you're in LG, you're in some vertex LG, and you get the list of your vertex, of the lattice that you're in, and you just add the vertex that you are on. So like to compute arcs, we want to get arcs list for the current lattice, append current vertex for block placement action. And for the other actions, you just do something else. So you need to be able to differentiate the actions, I guess. Or like, well, not really. But you need to make sure that in this specific one, the Minecraft example, you have all the 3 actions at every vertex. Always need to be able to jump in a new lattice. Okay, so the thing that we are doing right now is, it's not this, but figure out how we can use graph generating functions to describe specific structures in the world state graph. Figure out how to do this for the 1D Minecraft block placement environment. Okay, so this seems actually a pretty good topic. So if you do this more formally, maybe this would be pretty useful. Okay, yes, so like let's formalize the environment. Block placement. 1D Minecraft block placement. And then after that we want to generalize this probably. Do we want to simplify it? I think so. Okay, but maybe we want to think more about at the higher level what we want to do with this. So the thing is that what can we do with this? So what we're doing right now is doing the computing the representation of the worlds. We want to compute a model that describes what the world is. That is very small, even if the world's infinite, but by capturing the structure. Okay. We know that the lattice graph can be compressed in the sense that I can compute the representation that represents an infinite large lattice which is very tiny. There are other kinds of structures which are not lattices that can be compressed in this way into small description. Oh, that is interesting. It's interesting. Okay, okay. Okay, I think now we're done. Okay, with the variable. Yes, we're writing. Okay, it seems we can formalize this with graph generating functions. To represent a lattice, we can simply describe the connectivity around every vertex, as it's always the same. Okay, concrete example. For example, if you have a 2D lattice graph, we can describe this graph such a function which this can be operationalized by a function which returns the local structure around a vertex given the context the vertex is in. If you have a 1D lattice graph, this is very simple because for any context the vertex could be in, it will always, because the graph, okay, the graph generating function is, the graph generating function is just a constant, yes. Specifically, okay, maybe I'm writing this down too carefully. Maybe it's speech to text. So, or maybe, okay, what is it? What would be a constant here? Well, it would just say every vertex has 6 edges. It's constant. We just get generating function f. Okay. Okay, I guess let's draw a really simple example of a lattice. So here's a lattice. I guess I could do that, but I feel a bit, let's not do it. I feel like we need to do it in the morning, the first thing. But okay, let's think about these other graphs, because we can have also a graph which is like, I have no connections, then I have one edge. If I have one edge, then I have 2 edges. Wait, but it's always... Okay, this is what is the function here? It is like f of an empty graph. Okay, v vertex. And then we're saying something like, wait, what? But there might be no vertex. Okay, we need the starting vertex. Okay, and then we do g vertex and we say gen vertex is... Why would we have 2 edges here? Ah, here we have 0, then we have 1. I see. So we would say that... do we have length? This dot length and lean? Okay, it's sort of like, let's go over here and go into projects, learning lean. And now we do nix develop codium. Okay, maybe we need to, no, maybe not. Codium. We don't need this anymore. Don't need this. Okay, let's make a new folder about graph abstract. I want to have a new file which is about okay, these are terrible names. Okay, so let's see. So we have, well, let's check list.length. Okay, we have list.length. So we could say something like vertex.edges.length plus 1. Then we return a natural number, I guess. Which I guess we can write as this. Okay. Which is not really giving us the graph yet, but this is a good function, I think. So like for here we would have the function 4, but I guess the locality isn't captured. Didn't really specify sufficiently yet. What's the generating function exactly for lattice? Maybe that's easier. Or for line graph. What's the generate function for line graph? So we get this. And we're starting in the middle, let's say. For some reason, it works really well now. Okay, maybe I want to very briefly take a note on that. Right now, it works really well working with Ia, even though she's not saying that much. However, it feels like she's there. I'm using the technique where she's hugging me and touching me in order to make her presence feel. And this seems to be extremely useful for making me able to speak out loud. Though we are still talking, but it's definitely that I'm talking at least 80, probably 90% of the time. This might not be that much higher when I'm working with other people. I'm pretty sure I talk over 50% of the time. Line graph generating functions. Line graph generating functions, I guess. Line graph generating functions. Yes, I think it makes sense. So we have a vertex, and now we want to be like, give me the. Basically, this is like a lazy graph, I think. It's like, or lazily construct graph. Iteratively construct graph captures this more. Well, or rather, construct graph for one step. Style. Okay, let's do it. So like, we have a vertex in the graph. Right, we want to construct a structure around that vertex. So what's the structure here? So here we have like this thing. So, we want to do something like what? And they're both connected. So maybe what we do is we simply, in the simplest case, we just say how many vertices to add to this vertex. And how many vertices, and also how to connect it to other vertices, I guess. So I think what we need is we need to know this blue thing. We need to have the blue thing as an input, right? So we can say like, yes, we get a vertex. Okay, and then what we want to return is like a list of vertices and edges. Lol. Wait, that's it. I think that's it. Well, or even just edges. And so, would it make sense to return just the edges? It makes the code simpler, but a little bit less verbose. So let's do it. So literally just return edges. It's kind of funny. And then you just add the edges to the graph, and then it's done. And this is the general type signature possibly for all graph generating functions. Well, yes, if you don't have edge labels. Wait, but if you had edge labels, you could just return them on the edge. So actually it kind of works. It might be in the type of the edge. I guess we don't say what is the data on the vertex. Or, well, if we would write it like this, but the vertices would also be in the edges, then it also would work. So maybe this just always works, actually. Okay, yes, let's okay, so this is about like generating a 1D lattice. a major difference today compared to previous times when I tried to work with IA is that I took the meeting seriously. Even though I only slept 3 hours, I just still forced myself to stand up, and almost as hard as when I would meet with another person. I never did this in the past, which led to me not even starting to work with IA. Okay, now, okay, generating one the letters. Well, what did I want to write down? I forgot. Okay, so, well, okay, let's write down these notes about note that this might be the general type signature for encoding many different graphs you care about. For example, we can describe a graph solely by a list of edges, where the edges are pairs of vertices. Also, the edges could contain additional information. And because now the vertices are in the edge list, we can also make a vertex not just be an identifier but contain some additional data, meaning that now the edge list can also contain all the data about the vertices. This of course can also encode multigraphs and even hypergraphs if we simply have a list of lists of edges instead of a list of 2 tuples of vertices. Wait, not edges, but a list of vertices. If we have, let's write it as list vertex. Wait, in edge be list vertex instead of vertex. So we could say, well, that edge is just vertex times, oh, not that times, it's vertex times some type alpha. Right. Ah, yeah, and then it's like the edge list can contain the data on the vertices. For encoding multigraphs, hypergraphs, edge labeled graphs, vertex labeled graphs, and any combination graph type. This is because a graph can be represented by a list of edges. List of type, well, nice. Okay, that's really good. Really well written, I would say. Maybe too well. Okay, that's the implementation of this. It was just what we are saying now was just about how general this type signature here is. So, I want to say this vertex is like connected to these 2 other vertices, or like that's, so the orange graph right now, that's the thing we want to be able to construct. So we have 2 new vertices. So I mean, so I think now I'm doing something maybe that's not well, or like so, or maybe this is not that. Then maybe this is not completely general, because like we're now assuming a specific way to iterate through the vertices. For example, like this vertex is marked blue, by which I mean this is the vertex we're currently looking at. And we want to, as we generate the graph, only look at every vertex at most once, I think. So, in this case, so but let's just handle this case. So like I'm imagining this function gets sort of called, we're doing sort of like, it gets called for all of the nodes that it hadn't been called on yet. So like we're doing the operation, we're calling this function for the blue vertex, and then we want to generate sort of the local vertices around that vertex, and then we're not going to call it again for that vertex, but we're going to call it for these new vertices because it hasn't been called yet, right? So we need to keep track of that. So with that in mind, which I guess I want to, maybe I'll write that down later of how to use this, but that's what I'm imagining how we use it. We would now return, so blue is the V that we get in. So we would now say, for this vertex V, okay, now it is actually, we need to take into account, there's a special case for, in the beginning, this has 0 outgoing vertices. All other vertices we get after in this example will have 1 edge already. Like for example, if I'm calling it for this will have been generated, this connection is already there. So we probably want to do a case analysis on the number of edges for this. Let's see, let's just do it like that. Not sure if this is the best way to do it. So we match on, well, v dot, I guess the number of outgoing edges, so like edges dot length. We want to match it with either we have 0 edges or we have 1 edge. There's no other case in this graph. So if we have 0, then we're going to return a list. Okay, and now we sort of need to say like a new vertex. Maybe vertex to default or something. This is a bit weird because the vertex needs to have a unique ID, which we can't do in a functional programming language. You cannot have like the global state. Well, or I don't understand how to do it well. So let's ignore the problem. So we're going to say we have v, and then we get some sort of like vertex.new or something, or like vertex unique, like something like that. We want to have a unique vertex, like a new unique vertex that didn't show up before. Well, and we literally just do this twice. Well, and if it's fun, we just return one of these. Probably, well, it doesn't really matter probably, but in this case, probably vertex would be some structure, and then we would use these brackets if we want to do it in lean, such that we can omit specifying the projections. I'm actually not sure how we call it. In structure, we have named projections, and if we construct something without naming the constructor, we would name still the projections, but with this syntax, we don't need to name the projections. Okay. Oh, and here, well, this is a comma, of course. I think this is now just generating this. If we call it sort of, if we do like the thing where we like call it for all the vertices that were generated in the last step, basically. That would work for generating that graph. Okay, now let's do something more complicated slightly, which is, well, let's just walk through it briefly to see if it works. So here we do like return 2 new vertices, okay. And they're connected to that vertex. Okay, now we're gonna call it for this. Oh, okay, there's one vertex that's connected already. So we're gonna return 1 new vertex connected to that input vertex. Correct? Well, this is the same case. It's just mirrored. Okay, so it works. Now let's do a lattice graph that is 2-dimensional. Or maybe we can write down for an n-dimensional lattice graph, because like, well, that should be probably a parameter, or should pretty easily make that a parameter. Okay, no, that was not efficient to draw it like that. To draw it like this for the inside ones too. Okay, but anyway, that doesn't really matter. Okay. So we could just walk through how this works for this case. Let's see. So we have a starting vertex here. We want to capture all of the connected things around it, which would be this kind of thing. So basically, in the beginning we have no vertex, or like vertex has 0 edges, okay? And then let's just assume this is the same function above, and then we just say if we have 0, we return, let's say we have a function that gives us this, which is like connect new. So connect new makes this thing for n things, which would be 4 here. N takes in v. So v and then n new, which in this case is 4. Okay, now we have the case where we have already one connection, so we add 3 new connections. Okay, but now in this case it's not connected actually. Now this actually, we need something more sophisticated, unsurprisingly. Like this was not connected to this. But unless maybe... What if we sort of ignore, like we are generating all of them at the same time? Okay, now we are thinking, how do we connect? Yeah, okay, we still have a problem, I think. So generate all of these at the same time, but now, sort of if you think about what should be for this vertex, we're gonna consider this, this, and this. We want to add these as new. But if we would do the same for this, then we would be like, we add one here, and then like we add one, like a new one here that's different from the red one. That is not what we want. So, So this definitely does not work anymore. And we are not assuming that they have the structure, I mean the embedding. We can't check, oh, what is the vertex to the left of me? Or like, I mean, in this case we can do it. We can't do that in general. Well, unless we can have a function that in general computes the embedding for every vertex as we are generating the graph. Right, so I'm not sure if we can do this, or if this, would this work? I think something like that, we could just do it in this case. It would definitely work in this case. It feels like there must be some other solution that's like more general and still very simple. Maybe what we need, okay, we could formalize it. Okay, there are 2 ways in which you could do it. Let's write it down here. Okay, let's first copy all this stuff. Wait, no, I first need to write down. Okay, first let's write some quick notes. In the 2D lattice example, if we could compute an embedding for all the vertices, we could use this embedding as a context to depend upon, something like that. To compute a local structure around the vertex. Okay, but then it's like, note, this works for any graph if we could compute some embedding, that we can compute if there are vertices adjacent to us, then we can of course use this. Okay, and then there's a different thing, which is like, we can just not specify, well, right now we only get one vertex. But what we want to do, maybe, is to be like, look at these vertices over here, a bunch of vertices. And these vertices, well, we can just select more vertices. We can select more vertices that are connected. And then depend on that, something like that. I think maybe that would work, possibly in general. Currently, the generating function takes a single vertex as input. Instead, we could depend on a neighborhood of size n around the vertex that we're computing the structure of, which can be easily computed by doing a BFS of size n, of depth n. Note that this context will usually be incomplete, and the goal of the function is to, based on the current graph we have so far, infer what vertices in the graph are still missing. Or really just one vertex that's still missing. wait, one vertex? No, wait, that's all wrong. Okay, I'm a bit confused. Note that we could just return one new vertex, though. That's probably how it would work. Okay, so, well, this is actually BFS. I want to write this down. But just like this orange outline is the BFS depth 1 for the blue vertex, of course. Okay, now let's write down this above thing here. Okay, what is the idea here? It's like, okay, actually this is more like, not fine, this is how generating, this is about graph generating function. This is what you want to work up to. Wait, but maybe this is actually, oh, this is literally about this. Okay. Let's start doing this for one-dimensional lattice. Initially, we just start with one vertex, the blue one, and we want to compute the neighborhood of this vertex. Then, for each newly generated vertex, want to generate a neighborhood of it, and therefore iteratively unrolling the graph. We do this with this function. Okay, generating a one-dimensional lattice. And then probably we want to, wait, what? Generating, and then we want to, well, this is sort of like, I don't know, that's like an interlude. Yes, but how we just like sort of described, it's not sufficient. It doesn't actually describe anything. Well, it doesn't describe everything. Okay, now it's generating a 2D lattice. So does this capture everything we talked about? Sort of. Okay, now I took a break. Let's recap where we are at. So the general thing I want to figure out is the graph generation functions. So the reason why they're important is that we want to discover structure in a graph, in this word state graph, because discovering structure in the graph means discovering structure in the world, structure of the world. And well, the fact that there is structure implies that we can compress the thing, right? Yes, so but now we want to get an algorithm that gives us the specification for the structure in the graph, sort of. Well, or like, that's what these generating functions are, or what they could be, what I want them to be, I guess. The graph generating function is such that, well, it is a program which can construct a certain kind of graph without just saving the entire structure. It's like a blueprint, or like, not a blueprint, it's a set of instructions that tells us how to construct a particular graph. So, and we were thinking of this, and we have a one-dimensional lattice. We can encode it with this kind of function, and this seems to be pretty general as a thing, but now we notice basically the next thing. Actually, let's do a quick interlude, because there is another thing I noticed, which is like making a video. I noticed that it's doing something to my brain when I'm making a video with the intention of publishing it. Because then it feels like I'm talking to somebody, I'm talking to the audience. There is an audience. For example, here I was explaining this angle bracket notation, and maybe the explanation was so terrible that nobody would ever understand what I'm actually talking about, but it doesn't actually really matter from the perspective of how it is useful. Like, okay, wait, now I did some really weird thing with this transcription. But the fact that I gave the explanation and was giving it as if I was giving it to this audience is just a useful thing to be able to do, because that usually helps with your own understanding. And here I had the feeling that there is this target which made it easy to do this. It might be that having a publication intention is important, because then there really is like this audience exists. It's different from having a video on your hard drive rotting away. Okay, and now, actually this should be level 2 heading. Wait, no, level 3 heading. Okay, and now the thing is though, generating a 2D lattice. So that was the next thing we want to do. We could like reflect on whether this was good. I mean, whether this is now a good thing to do. Because like, well, the thing is that the previous method for the 1D lattice is definitely doesn't work exactly like that. Okay, and so let's see. What seems the most useful thing to do right now? Maybe let's write it in here. Okay, so we got more clarity on what would be this generating function and why it's useful. Although I guess I didn't really explain why it would be useful. Now, does this still seem like the best thing to do? Okay, let's briefly scan over these things we were talking about before. So before we were talking about, oh yeah, what would be the general algorithms? Now we're doing something, but what would be these like hard-coded algorithms? Now we're doing something that's even more general, sort of, because we're trying just to figure out how can we describe graphs. I guess something like Solomonov induction, but instead of thinking about describing the world exactly, we're just thinking about describing some graph structure. Yes, I think that makes sense. Yes, okay, I think this is the best thing to do. So, okay, yes, we want to do that. So now what would be the best next step here for the generating function? So we could also think more about, we could formalize more the very simple example that I wrote on a whiteboard. We could like add, because here's the thing, there is the wrapper function, it calls this. But this is pretty clear how that works, I think. No, I don't think we need to write that down. Yes, I think let's figure that out. Okay, let's figure out the lattice. So, well, let's start by sort of correcting the type. Now we have like a different thing. So let's just think about this kind of graph. But now we want to. So what we could of course do is we just take in the graph also, and then we just do the BFS or whatever we do. We do it in the gen function. But this is very confusing now, I guess, because like it would be the graph that we have so far. Okay, then it would maybe even be a bit helpful to write down the wrapper function. Our wrapper function is completely the wrong word for this, but the like surrounding the caller thing, the actual graph constructor, the like graph unroller, we call it. And we could pass the results so far just in, and that would kind of work, but I think that might be too complex. For now, let's just, because then we need to deal with some edge cases, like if we start with one vertex, how are we going to do anything? If we want to actually like have like some BFS of depth 5, like then we start with like some BFS graph like that. So I think it would be simpler if we, for now, just say we get a graph of a certain size. I think you could probably encode this as a data structure. So there could be data structure of depth n BFS. Well, okay, this is a bit weird. What I mean is, we could have something which is something like graph, vertex, natural number, and this is actually, this would be a type. So I'm saying as I use dependent type. Oh, I'm using a dependent type, okay. So we could have the dependent type of the induced graphs. Okay. Ah, okay. Yes, okay, and this actually would represent sort of something like we have the thing where, well, I guess this is a structure, right? I guess it's a bit strange. I don't quite understand how would, for example, lean right is actually down in terms of property. But what I want to say is like we have these three things, and then we have sort of like well, you have this property holding. If you take like the G, the vertex, and the natural number, then we will have it that if we sort of say BFS of G dot V for n steps is sort of equal to G, and at the same time it's like the BFS is just stopping sort of like can BFS for n steps. Okay, this is terrible, but it's terrible. That doesn't really work. The camel case. Wait, this camel case, Pascal case, I don't know. And then with n on this using this I guess like this is the starting vertex, and then I guess you also have like the graph path and it's equal to the graph and it's equal to n. So we check like can we still unroll? Like basically we unroll the graph until there are no more edges to unroll, and we stop. Yes. Well, and then we have counted how many BFFs we did. That's what this function is. So like the n is as well as possible is what that gets us. Okay. Well, okay, now I have some type of what is this again? This would be the type of a subgraph. Maybe using a type is the wrong way to do this. Okay, but what do we want to say? So we want to say that we are getting... Ah, yes, the reason why I was doing this is because we want to get this type as input to a function. Like this is a BFS graph, sort of, okay, with like this property. Okay, and now we have this BFS graph. Now we can define a function like this that takes in a BFS graph. That's the idea. So instead of getting a vertex, we will get a BFS graph around the vertex. I guess if we want to do it like in lean, we would use underscore. But it doesn't really matter. So, but we get, okay, maybe I should leave a bit of a room for what we want the function to call. Well, I guess we want to just call it gen. And now we get the BFS graph, I think. Yes, I think this makes sense. BFS graph for some sort of parameters that we don't yet know. We don't, well, or like we know the vertex. Okay, now I'm a bit confused. I mean, definitely it's not necessary to encode it in types like this. I'm just trying stuff. Let's continue to try it with that, but I think it is a bit weird because we would definitely need to even say what type this is. In the type signature, we need to already take in a vertex, unless we know exactly the vertex, but we don't. We might know exactly the natural number based if we just want to encode this thing. But here sort of, I guess we need to still have a vertex, and then we say the BFS graph. Probably there's a better way to say this. With a V applied, and something here, which is probably upper bounded in this case. Well, upper bounded based on the dimensionality of the graph we're constructing. Okay, but let's continue. Let's not get stuck too much in this. So let's see, a list of edges I think is still sufficient. Right, yes, so like a list of edges, yes, like what we were talking about before, about how general that is, list of edges. Well, that's what we were actually saying. We were actually not talking about when we were talking about how general this type signature is. We're actually talking about the return type. Maybe that's a good thing to mention. So we still have a list of edges. Okay, and now we'll go through this concrete example. Let's work it through the lattice example. Well, okay, I mean, that's what we are doing. and see, given that we have let's say we just have the BFS graph of depth 2. Well, no, depth 1 actually, right. Depth 0 would be 1 vertex. So depth 1 gives us the 4 vertices. Now, given that we have 4 vertices around us, so the idea is, the thing is that this is incomplete, right? Actually, this type signature therefore doesn't already make sense, because this is incomplete. We're not getting the correct BFS graph. I mean, actually we do get some BFS graphs, so actually type kind of does make sense, but it is sort of like, it is not the BFS graph in the final graph, because that's what we want to construct. So, okay, let's just see how this would work. So let's imagine we just constructed, like, for the first vertex, the thing. So we already, so we start with, okay, let's do an example. Let's do it, let's just do it over here. So we start at the vertex. Okay, let's use blue again. Yes, and now we enroll it into these vertices. We assume we have already magically somehow knew this is the correct thing. Okay, and now we do the BFS of depth 1 for this vertex, let's say, which would obviously be like this subgraph. And now we want to be able to calculate what, okay, here's the thing. Is it sufficient if we manage to construct a graph around this new vertex here, such that the connectivity is correct for all the vertices that already exist in the graph? Well, I mean, obviously, yes. if I think about it very briefly, then yes. If we always add a vertex and then we connect it such that the connectivity is exactly the correct connectivity, well then this graph now has exactly the right connectivity, sort of, for how far it is unrolled, right? But not assuming that we have like a finite BFS. Like maybe the connectivity is such, like in any graph, not in this graph, but any graph might be like, yes, this vertex that's way over there, you need to connect it to that. But we don't need it here, therefore we can use this BFS graph notion, I think. So what's the connect? Okay. So like this, okay, we do this, now we do the BFS, and now we start to generate new vertices. Okay, generation. We definitely want to generate these somehow. We want to say generate these green ones. Okay, and then sort of like, possibly this is a separate step, where like we have a separate step where we want to say, please add, like, yes, this is the difference to this thing. Because here, in this line graph, it was sufficient to just say, generate for this vertex all of the vertices that we, immediately, like just, like this vertex, what new vertices do we need to make that are connected to this? And we're done. But here, there's an edge here between these two vertices, for example, which wasn't the case here. This step was just not required. But now we have the required step of like, also, the vertices that were created, we need to connect them correctly to the vertices that are already in the graph. And the thing is that we don't have this embedding. We can't say like, this is the right. Obviously we need to connect it to the right because it's a lattice. So, and clearly this is not sufficient because the BFS is not sufficient, right? Yes, this vertex is not contained, yes. Okay, if we increase the BFS, then we have this vertex. But how would you know that we need to connect these? I mean, I guess what we could say is 2 of the newly generated vertices need to be connected with 2 of the vertices in the BFS. Would that just always work? Let's see. So we do depth 2 BSF actually. So we get this. Yes, we get this thing. So now we need, we could say 2 of the things need to connect to 2 of these. But okay, let's just do that. It would be very funny if this just works. So, okay, yes, connect this. But it could be this, right? But we could sort of swap them and get the same embedding. So it doesn't matter. Ah yeah, if you connect here also, yes. You can also swap it. So that's correct, okay. Let's do the next step. Let's see if it's correct. So now we get this graph. Yes, so far we have generated this graph. And I guess now we want to look for a counterexample. Is there a vertex such that this procedure breaks? So it feels like if we do it here, then we would get the BFS would be exactly this thing, which, wait, not this of course, but this also, including this, which is, well, if you just look at this graph, well, it's exactly this graph. So we add these green vertices, connect them to, it doesn't work because there's structure here. And this structure we need to take into account. We want to say, look, we cannot connect the green vertex to this one. That would be wrong. So somehow we need to say, yes, okay, so that is, so here if we pick any vertex are symmetric, always works. So here we need to do something new. Let's check maybe the case if we are here. If we are here, or like it's marked, so like this would be when we check if we want to generate this vertex. But what if we want to generate this vertex? Now the structure is different. Actually, structure is also different sort of in lots of places. Also the thing to keep in mind, I guess, is that at some point we will have some sort of, well, we could also mark. So if we could mark that this vertex has been generated, this vertex has been generated, this vertex has been generated. So like we won't go through it again in the search, in expansion. This will not be expanded anymore. So the algorithm just runs on all the non-crossed out vertices. Yes, and this is the same as this and this and this. It's all the same structure. So we only need to handle this. If I can handle these two cases, then it would work for that thing. But okay, yes, as the first step, let's just think about the BFS of depth 2, I guess. Which would be this thing. It is actually very similar sort of to this other thing here, which is this like cross thing, but we have an additional vertex here. Okay, this is certainly a lot more involved than I thought. I thought there was a very simple function which would just generate locally the vertex. But it does really feel like this is the right approach. Like this algorithm so far is really about infer the structure, generate the structure, generate a graph. The algorithm generates a graph of environment. Yes, yes. Why I say this is because to contrast it with the edge labels and stuff. Yes, and word states, which you might use to generate this graph also. But right now we're just thinking about how to capture the pure structure of the graph without the additional information of like what are the actions, what are the environment data, what are the word states, I guess that's the main things. Okay, so I'm pretty sure, or maybe this is not possible, and I think it's probably possible to do it like this. So let's continue. I think this is a good approach still. Well, okay, the very obvious thing that we can actually do, which would be very simple, is just increase the BFS. Because if we increase the BFS, this is actually structurally dissimilar from this. And this is structurally dissimilar from this. Now we can actually differentiate everything. Actually, in some sense, we don't even need to do BFS, because we could also say like, yes, like search now for vertices that have two, and here's a different way, two connections, but here's maybe a different way to think of this entire algorithm. Maybe it would be like, it is like pattern matching on the structure of the graph. Okay, let's write this over here. We can think of a pattern matching, in a graph. This might be actually related to category theory now, because that's what it is, based on my limited understanding. Well, or at least a diagram. Well, maybe this is slightly different actually, but I'm not exactly sure. But so, okay, the idea would be in this specific case on the whiteboard, yes, so let's define the algorithm sort of, we have a bunch of patterns basically is what I'm saying. And we could sort of say, if you observe this pattern, which, okay, maybe it would be even simpler if we increase the size. Let's see. Also, where we want to be careful about the permutations. Which order, or like should be like, if we have some iteration, the algorithm, the iteration needs to be well specified in the sense that it's not like randomly iterating in such an order that like our algorithm works. We want to have it explicit. Maybe, yes, something like that. Okay, what are the patterns here? So like, okay, what's the pattern in, okay, let's go over here and think of this as the pattern thing. If we have this line graph, and I have some center vertex, I wish to remember not to steal all my markers always and bring them to my table. Okay, here we have, if this is the center vertex, I will go over here. So this is the thing that we're matching on, which is a vertex without connection. Okay, this is a bit confusing how I wrote it. Let's write it a bit differently. So we have some center vertex, and now given the center vertex, you have sort of this pattern of what is to be added. So the blue is the match, and the blue is the matched. Is this the right? Let's say blue is matched, purple is added. So we add these. Are these colors easily differentiable? Maybe not really. Let's pick the best colors, which is, I guess, red and black. So black, let's say black is the match, so we get this. Red is everything that's added. So this means, given we have a vertex with no connections, give me, add two vertices to it. Okay, that's what we do if we have this case 0. Now, case 1. I guess it's literally just the case 0. So case 1. Well, case 1 would be. Okay, and now we need the center vertex though, the center vertex concept. So let's wait. Is this? That's not so good. Okay, let's use for the center vertex green. So green is the center vertex. So in this case here, we would have a center vertex. So this is the vertex that we want to expand. Then we have a bunch of structure on the center vertex that we want to match. And in this case, it would be, we get this. Meaning the center vertex has one vertex connected to it. Okay, and then if we have this, then actually we could now also add structure to this other stuff, which is interesting. It's really obvious that we can do that now. So we'll get this. Like here add 2, and here add 1, given that there's this structure. And now we could also say yes, given that here's add also some other vertex here, and then we wouldn't get this graph. Actually, let's do that. Let's think about this pattern. Let's just think of some pattern, and then what graph does it generate? That's interesting. So then this would be this case. So what if we have the pattern which is, so obviously we need the center vertex. So but let's just do this pattern. That's just set. So it's the same as the one on the left, except that over here we also add a vertex here, like this. So that means that this connects over here. Right, okay, and this connects over here. And okay, this here. Yeah, and the edges the edge color is also important, right? Because well, we can match on an edge, or we can add an edge. We could for example, here's a funny little graph, or with funny I mean extremely trivial. So here are some patterns. Let's just write this in a moment. But like we could now also imagine the graph, which is, so basically we can just generate an infinite graph that has no edges of just vertices. If we write that we have the matching vertex, and the matching vertex just adds a vertex. Okay, that's very simple. So let's just run the expansion for this first. So this would give us something like, first we place this vertex. Okay, now we use the pattern. We're like, aha, it looks like, and the patterns would be ordered, right? These are separate patterns, and we apply them sort of like first apply this, then apply this, and so on, I guess. Yes, like pattern matching, but exactly like the pattern matching here. So now, we place this, then we place somewhere another one. This is the red one now. Well, now for this red one, so this is now eliminated, right? So this is like, okay, was matched. And now, okay, now we have only this one to match. Now we're like, okay, let's place another one. So somewhere, okay, this was matched. Okay, for this one, place the graph somewhere. Okay, this was matched. And we repeat forever. So we generate just an infinite graph a graph with infinite number of vertices, no edges. Actually, now I realize what I was saying about before about the generality of the type. It does not work for disconnected graphs like this. We can only ever describe graphs that are connected. Yes. So what is this other pattern over here? So we have this pattern. So we know what this pattern is. It's just a line graph. Okay, now let's do this graph, which is, well, like, let's assume we start with a single vertex. I mean, you also need to assume that if you give it no vertex, well, it will just always do nothing. But it will be like, here's the empty graph. That's what it returns. Yeah, it can never actually, any of these pattern matching sort of algorithms, descriptions, well, it's not the algorithm. It is any of these pattern matching specifications would be such that if we don't give it an empty graph, it would return an empty graph. So, okay, so we start with some vertex. Now we add two vertices to it. It's I think good if we label it. Maybe we want to even label it as 2. Yes, I think that would be better. Let's label it based on the step, like the matching step. And we could label it based on matching step 1, matching step 2. I think probably in this case it's not necessary. So we would have basically just like 1, or like I guess we have 0, which is the initial configuration. So 0 is like starting vertex. Oh, and this is interesting because yes, these pattern matching specifications, they actually, oh, this is really, okay. The thing about these pattern matching specifications is that note that these pattern matching specifications are compositional. Or compositional is not the right word. Are parameterized by default. They can always, I can always start with a graph G and then apply a pattern matching specification to it. Pattern matching specification. That's the wrong word. There needs to be a better word for that, but for now let's don't bother. Given an empty graph, any pattern matching expansion, yeah, maybe that's a good word, pattern matching expansion. Any pattern matching expansion returns the empty graph. Passing a single vertex leads to the graph that's completely determined by the pattern matching expansion. Pattern matching by the patterns. Pattern matching expansion, it sounds like the algorithm. By the patterns. But we can also just input an arbitrary graph that would be different from the graph generated with one vertex and generate potentially very different kinds of structures. I'm actually somewhat confused, like how different the structures would be that could be generated. Maybe I want to have a concrete example here. So if I just input a complete graph, for example, I could start with a complete graph of size n and then apply the pattern matching for a line graph, which would not change the complete graph at all because nothing matches. Okay. Okay, and here's the thing. Okay, and here's, so, okay. So, yes, so like, imagine I'm starting with an infinite line graph, and now I apply the pattern matching of the line graph again. Note that in this application of the pattern matching, we are not we have not marked any vertices as traversed yet, and therefore we will get a very different graph that's not the line graph. Okay, that's very interesting. So actually let's think about that first. So this is actually not a section. This is like pattern matching or structural matching, structural match expansion. Yeah, that seems like an okay name. Structural match expansion. So what if we first generate a line graph? Or yes, let's write first the example over here. So like, for example, we can generate an infinite line graph by applying the following patterns. Okay, and so like the green vertex is the vertex that we want to expand. A black vertex, a hollow black vertex, is specifying a pattern. In the above, it means that the green vertex needs to be connected to one other vertex. The red vertex and edge specify the modification we want to perform. Meaning, in the above, we want to add a new edge and a new vertex to the green vertex. Okay, and then this is okay, I think I discovered a bunch of nice stuff. Just okay, so like so here's the thing we can do actually, which is also interesting, which we haven't thought about, but here's a new kind of pattern we can have. I'm not sure how to write it. Let's just write it here. So there is a pattern that adds edges. So the minimal example might be something like this. But actually now I'm a bit confused because we don't necessarily need the center vertex. Okay, we can do it with the center, but this is also an important point. Non-center vertex expansion. Maybe this is a lot harder to do, but okay, now so let's not talk about it right now. But here's an example of the thing I was thinking about if we use center vertices. I mean, very simple example would be, so we have a center vertex and then we have the following structure. Maybe this is actually important also, or useful for the lattice expansion. Oh, okay. I could certainly make it such that we add these edges here. Like that's a possible thing we can do. We're like, oh look, here's this like thing. Add, like complete the lattice. This is sort of like, look, I have this partial lattice, this exact partial lattice completed. Which seems very likely to be very useful if we can do something like that. It's like, look, complete the lattice. Then it gets us the lattice, the like expanding lattice structure. Like something like that seems like might be pretty good. Like this is like expand for a single vertex. Yeah. Okay, this notation is really nice compared to writing it like this. We can basically, you could also have like only a single edge. Or like here's a different example. I could like imagine we have this. This is center vertex. So what we would do is we would see that we have these 4 connections, and then we could say something like, oh well, just complete the lattice like this, sort of, and then we get square. Okay, we can just reconstruct the lattice now. Something like this. So like this is one pattern. This is a pattern, but like, okay, now here's the nice thing. Let's just write down the lattice construction, because now with this we can easily do it, I think. It's my intuition. So we have this pattern. We also have like the 2D lattice, I mean, of course. We have this pattern. We have the single vertex. Then we construct this, basically. That's what you can say. Please add these lines. Okay, now we get this. Now the next pattern we need is if I see a square. Okay, I'm somewhat confused about this next pattern. I think it might be something like I mean, maybe this is even a lot simpler. I mean, this is possibly not the simplest pattern, but one way to do it would be like, if I see, pretty sure there's a simpler version, but if I see this, let's say that this is the center vertex. Now we sort of like, no, this is like at the edge. You do this, and let me see, we add this. Okay, because this is now like odd and even or something like that, number of vertices, I think there might be some problem. So here we can just now add this, no problem. Actually, yeah, and then we can add it above. Like this can be rotated, right, to match this. Okay, we do this. Yeah, that's like, how could we match this? Well, in this case, we would just expand, 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 expand. And now where can we match it? So, well, okay, let's just write it. So we start with the single vertex. Okay, then we do this. But then we do, of course, this. Let's just write it like this. Then we do. Well, okay, I think this is not so good to write it. Let's from now on write the added thing as the red thing. So we would add this and this and this and this and. So can we match somewhere again? Well, so here's also a thing. Yes, okay, would this match somewhere? I mean, obviously it would match here, but we already generated that. Let's see if I'm doing something in my brain that makes this generation easy. Like I'm doing some implicit step right now, it might be possible. If you just apply this in a dumb way. This definitely never matches, yeah. Then this thing, well, obviously matches here, we get this, but now does this match somewhere here? Also, I guess if it were lattice view, this is a much better way to write it, much quicker. So these are the new vertices. Okay, actually let's redo this with better notation. So first, okay, let's just do the entire thing. So first the notation. Okay, now I'm a bit confused because we definitely need to say green. Yes, okay, if I have a single vertex, I obviously still want to draw it like this. Okay, and now here's a bit confusing because do I want to add the vertices here or are these just edges that I'm adding? Actually, that's ambiguous because I could just match on the edges. And actually, we cannot use this notation really. Or it does merge some things that might be bad to merge. Note that we can just specify a single edge without a vertex to be matched, or even a disconnected vertex to be matched. Okay, let's quickly write down an example of this. This is actually ambiguous. This could be read as any of the following. There exists another vertex in the graph. There exists another vertex in the graph that has no outgoing edges. Well, or just edges. Okay. Yes, okay, the example that was actually not about the example I wanted to make. This is interpreted as we match a vertex that has 3 edges and to that vertex add 5 new edges. It becomes even more ambiguous when we are modifying the vertex not connected to the matching vertex. Okay. I took a brief break. Let's see very well. So I have the structure matching. Yes, that seems good. Edge. It's so short. It's so short to explain. The matching algorithm takes in the current graph, then a list of these patterns, then tries to find, for the first element in the list, all the matches and applies all of the expansions to the graph, and then does the same for the rest of the elements in the list. That is how you unroll structural matching expansion by one iteration. Right. Boop. So let's see. Relation to category theory. Okay, and wait, structural mesh expansion. That's definitely part of this. Also, okay, yes. So, I think we were just about to basically working through a bunch of expansion examples, and we wanted to check, sort of. Well, we want to just construct a lattice now with this notation, because I think it should be pretty easy. I also noticed that actually there's another thing which is kind of nice. I just noticed implement or like front end or like UI front end, or it's like we can use this specification language in order to talk about how to construct specific graphs, as the specification is simply a graph with some specific labels of whether it's a center vertex, something that we're matching, or something that we're adding to the graph. We can use any UI framework that allows us to create a graph with some data on nodes and edges, which I'm sure there exists many. So let's do the lattice graph construction. So we had this thing over here. Okay, let's figure out how to do these pens. I probably want to uncap many of them because I'm using so many colors. So many colors, 3 colors, very many. Okay, and now what we can do, I think, is... So first of all, like the pattern was like this, right? Like these were the steps. This is not written down in sequence. Okay, so we do this. Okay, and now let's erase this stuff here, make it more clear. Yes, let's do that. So we're just applying this pattern here, where we would start with the center vertex, of course. Yes. So we have a center vertex, and then I'm really confused how I should handle these pens. So we go to the next step, where we have okay, now, well, let's not talk about the center vertex here because it doesn't really make sense, because I want to talk about I apply this pattern as much as possible. Let's just say we have a vertex. And then the next step, though, we want to sort of say which vertices we get additionally. So let's still use red for this, but these are different graphs, sort of. So we use red, and then the next thing, this becomes the black. So red is just the things that we added as new things. So here we would do this thing. And then we would, then that step is complete. So of course we get, yes, I should be more consistent about when I fill the vertices and when not. But we go to this step. Okay, let's maybe make it slightly less ambiguous by using this double arrow. We're doing a bunch of steps here. So now we're adding, now we use this pattern, so we add these things. And now we will add these patterns. So we get this graph, and we're adding this. And well, we also have this, of course. And now we also sort of, okay, let's actually use the notation of which vertices we have matched on. If they're filled in, we have already matched them. So this would not be filled, but here it would be filled. And so like now these would be filled. Maybe let's write this in the notation thing. Ah yeah, so like the thing is, this is a completely different notation. Now this is like a graph construction notation, I guess. Okay, maybe let's make it a new heading. So this is about, well, what's it about? Iterated graph construction notation. Or annotation, I guess you would call it. So, well, filled black vertices have already been matched. Hollow black vertices need to be matched. Hollow black vertices are currently being matched in this step. Red hollow vertices will be added in this step. Yes, I mean that's the thing we have so far. So we could also use alternating colors, I guess. Okay, now here's a weird thing, because we actually won't get this structure over here, because this vertex has already been matched. So this is actually not what we get. Is it? No, wait. In this step we're matching here and adding this. Yes, okay. That is very... So in this step... Okay, I think this notation needs to be slightly clearer. Because like here, we're not matching on this, we're matching on this. So these are like crossed out. Okay. Filled black vertices are currently being matched. Filled crossed out black vertices have been matched and will not be matched anymore. So let's think about, well, or let's just write it down. So we have matched this, we have matched this, we have matched this, we have matched this, we have matched this. Now we will be matching, wait, what? Okay, here's the weird thing. This has been matched, this has been generated, but it is not matching anything, right? This doesn't match any pattern. So we won't generate it. Well, we won't generate it? Like but it's still open. It's still open to be matched. Which potentially, okay, here's the thing. It's like, should these be blacklisted? Like the ones that didn't match. Like in some sense, it feels like if we could do this, it might be good, because then we just get smaller and smaller in the number of vertices that we need to match. Yes, so we only ever match sort of on the boundary. That's kind of nice. I mean, I'm pretty sure we can exclude them at some point. Yeah, so I think at some point we can say, look, like intuitively, we were like, look, we're already over here in this graph to generate this entire thing, and it doesn't match anything. But it doesn't change anymore. At least if we are... Yeah, at some point we can say, look, the structure is this large, and therefore it didn't match so far, it will not match in the future. So it's like, we want to blacklist them when no pattern matching could change. When the structure couldn't change to affect whether it's matched or not. So that we can get a pattern match. So that we can't change the property that we didn't match. Such that the did match function or did match check can't change in value. Okay. Yeah. Okay. Okay, this is nice. Okay, now what do we match here? This we don't match definitely. Do we match this? We do actually match that, which is wrong. You can't have that matching. Because like you see here, oh, we can now like just patch this that it works. I think by adding a step before that, which is pretty nice if that works. Like here we would match with this pattern and then we would add like a new vertices in like a way that no, we definitely don't want to do that. Wait, we actually do match a bit weirdly. For example, we match this thing. Like if you notice this pattern here, if we look at this vertex, it actually matches the pattern. And then it just like, whoopsie, like, or like, like in this step, this is a match where we would fill in something here if we use this pattern. And the same for here and here, so that we could get a square again, sort of. Which is pretty nice because it sort of connects back up the thingies. Okay, and now we have these. So then we would, if we, the problem is we could also match here. So we have 4 vertices. These 4 vertices also match this pattern. So definitely this pattern would need to sort of come before that. But the thing is that this pattern also matches here. So let's just change the ordering, I think. I mean, if we change the ordering in the following way. Okay, so here actually I was talking about before this, like, what does it mean that, well, this center vertex has no edges, like that we're matching, it only says a bunch of edges. So we could interpret this, which would kind of be the natural interpretation of this vertex has no edges. And if that's the interpretation, then we can definitely do, then we can just reverse the arrows. Then we can say this is the first matching pattern, then we match this, then we match this. So if we do that, here we would add, well, this thing, we would add this thing, we would add this thing, we would add this thing. Okay, and now we of course though, and like, okay, it's a bit so like these are the vertices that match that, but maybe now they should actually be colored red because we have multiple matches. Or like, well, it's a bit, this is a match. But now we also have a match over here. This is a match, but then we have sort of, in the same way, a match over here. And also a match over here. Or like, match with match now, I mean, this is things we would generate if we just match everywhere. Here we wouldn't do it. Would we? I think we would not. But we would definitely generate like stuff like this. And now this blue is a bit weird. Well, this is like vertex. I'm saying like there's this blue inference which infers but actually we don't have the blue one because we don't add this vertex yet in this step. So we could sort of, we definitely don't match this because this is also red. So we don't get this. But so actually we don't, well, okay, we literally just match one pattern. Okay. Okay, so we would add these, we would add these, we would add these, we would add these, we would add these. It would really just like really grow this lattice. Okay, this is what we get. And yeah, we're actually matching there, we're matching there, we're matching not there. So the next step when we match here, we would add another vertex. So because the graph is so large, maybe let's do this with a different color in the same graph. So maybe erase this line here. Yeah, okay, but if we do that, then I think we need different colors for these things. So maybe what I want to do is just, well, can I copy that? If I copy it in a digital thing, I think it would be good. I'm remembering to put my pens not on my table. That's good. Okay, let's try to do it digitally. Okay, so let's see how we further expand this graph. So I guess somehow I want to repaint these to black. Okay, we can do this. oh, we can do this. We can do saturate minimum. Okay, we do that. Wait, so only we want to do the copy. Wait, it was a copy. Okay, so we get this. And now it's a bit small. I think it's better if it was a bit larger. Maybe like this. Right. So we got this step, and so well now we can just cross out all of these vertices, or maybe let's do it like that. So and now we are not matching anything. Let's keep using this color. So here we are matching. Here we are matching. Here we are matching, of course. Here we are matching. Here we are matching. Okay, it is exactly we're expanding the thing. And oh, we also match here, of course. And we do this. The thing that I'm omitting sort of is that when we're matching this thing over here, what we actually do is temporarily is this color. This is the thing that we're matching, and then we are sort of wait, this is wrong though. I think this is the structure we are matching, but this is different from well, here the matching rules. So you see, so if we copy this structure out, this blue structure, let's maybe actually remove it for now. Maybe do it on a new layer. So if we have this blue structure, well, it would actually happen. So it was wrong even before we did this step, I think. So we can move that. Let's see, where did we mess this up? So this is definitely correct that these things are added. I think the problem is over here. We added this thing, but let's analyze the structure. So if we have this thing in here, what we said that we would do is to, the important region is this thing. We're sort of saying, well, actually not this, but this is our matching region. So maybe let's do it in green. But I guess it was usually black. Okay, it's a bit confusing. Let's do it violet. This is the thing we matched, and this is the thing we sort of construct, which means these are also constructed, even though they are already there. Which, of course, well, or like, of course, it isn't clear in the formalism that we've written down so far how we want to handle that specific case. And I think by default, the default assumption, I guess, that I would intuitively seems most sensible is that we simply match exactly the structure. And to be able to have exactly this structure over here. Exactly this structure. Exactly this structure. So like there are no edges that are coming out here. That's what we want, I think, which then means this just doesn't match even here. It doesn't match here because here are a bunch of edges behind, right? So I think we need we need to extend this notion. We need to say things like, this can be there or this cannot be there. Like, I don't care if there can be an edge here or there cannot be an edge here. I think that's what we would need. Well, or like, yeah, I mean, otherwise, in this case, it wouldn't work. Of course, we could have sort of a vertex where we say, we don't care about other, like there can be more edges and we don't care about them. That would be one thing we can do. Another thing, which is sort of, yeah, this is sort of like like there are multiple things that we can do now, I think. Okay, let's do it again on a whiteboard because it's small again. So we could say something like, let's see. So like we could have sort of like, let's say we make it for now triangle, and then we specify some edges to the triangle. And that means that there can be additional edges which we ignore. Any number of sort of like additional edges are irrelevant. We're still matching. So like this would mean it has at least two edges basically, I guess. Yes, that's what it would. And if we would replace in this pattern over here all of the black vertices with triangles, and that kind of would work. So what we could also alternatively do, so here we have like this 3 thingy thing, but do we actually need that? What about this thing? Like what about, okay, given that we have the triangle notion now, what about if we have the pattern? The pattern is simply, well, I have the green, so I have the center vertex, which is a triangle. Not even sure, I'm a little bit confused about this notion of a center vertex, if we actually need this. But for now, let's do it. And then we say we're adding 1 vertex. So now, if we just have this be our rule, how would this work? So we start with some vertex, and then we add a vertex. Oh yes, we add exactly. Oh, okay. This is definitely not what we want. We add 1 vertex, and now we have matched this vertex, which I mean, it's not complete, kind of, right? Then we add this again. I mean, this is now sufficient to specify a line graph. We don't need to have these 2 patterns that we had before. We can use that to match the line graph, to generate a line graph. Like that, this is now done, and so on. Actually, this is not a line graph that goes sort of in both directions. This is the line graph that just expands into one direction. Which probably, actually we can just write it down in the previous thing here also. So it's actually fine. Okay, and there's even more notions that we could have. So we have the triangle, but what we could also say is like, don't blacklist things. So what if we have like a half circle? You could have the half circle thing, and that would be like, for example, this would be like, always match the pattern, even if you matched it before. So never blacklist. If we do something like, okay, that would mean if we do this, we have this vertex, and now we say connected to 1, new one, then we would get something like this. So start out with a vertex, and then we say, okay, so this vertex, well, that's the number then. That would be easier now. So we have 1, and then we or like 0. We start with, so this is the initial thing. Now we add 1 over here. Okay, makes sense. But now look, this matches again. We didn't blacklist any of these, so we get actually that we, in step 2 we add new vertices to both of these, and then in step 3 we add everything over here. Well, over here, I mean, there's something like this, which seems it will generate some form of tree. Okay, let's start like that. We can see the tree. So 0 would be the root, and then we get 1, we get 2, 2, and we get 3, 3, 2, 3, 3, and then we add sort of like 4, 4. Wait, is this right? So we definitely added 4 to the 0. The thing is, yes, the 4 gets added also to this, to everything, except, so also here, 3, 4, to generate sort of this kind of really imbalanced tree. So by each, so in any layer we have sort of like, we have n children, and then, like we have a tree. Okay, the actual pattern here, this is also an interesting pattern potentially, I guess. So it seems like this is the tree, where we have the pattern that any node has some number, and based on the number, it has that number. Okay, we have some n is some parameter of this tree, and then we say that the root has n children, and if we have n children with like v dot data, whatever, or value, being sort of like v dot data comes from this list, like 1 to n, and then actually in general any node has a value, and it has n number of children, or wait, n? it has a little every node. Every node has node dot value minus one. No, node dot value. N minus node dot value children. And this is basically what we're constructing with this. Well, I mean, now I have sort of this, but without any labels, which is, I guess, sort of interesting. Like this specifies this, but like you don't actually need to keep track of all the labels all the time. You only need to keep track of actually of nothing. You don't need to even keep track of which vertices you visited because this matches any vertex, and this is just about we don't care about if we visited them. So this is like this, but specifying it without all of this like stuff. You need to write this stuff, and but here, if you know what this means, it's sort of like it specifies the same kind of thing, but without anything. So like any additional data. Okay, let me write down all of this stuff. Okay, so we got this thing. Okay, we'll just have the example for that. Okay, now how do we structure graph generating function? But then we have structure match expansion. Yes, edge matching and yes. Okay, edge. Okay, and then what we also want to have is sort of like we want to introduce these additional things. Let's see. Match types or match types. It's called something like that. Match types. Okay. Now what do we have? We have arbitrary additional edges. We got no blacklisting, and there are a bunch more, of course, that we can do. Actually, I think it might just be complete now. So, because if we just have a normal vertex, then we can sort of do this like edge matching, where we just have the edges. But we could just draw like edges without vertices 3, and that means we have 3 outgoing edges. And like we could make it such as we don't draw the edges or something, but it doesn't really matter. Like the important thing about this triangle thing is that we can specify. And I guess the thing that we couldn't specify is sort of a range of edges. That might be something. Range of edges. And arbitrary additional edges is, I guess, sort of like it's not bounded. Well, I mean, it seems like a special case. When we draw a vertex as a triangle, it means that this vertex matches even if there's an arbitrary number of additional edges that are not drawn. We can then still specify a minimum number of edges. Range of edges. Yeah, it might just be not that important, range of edges. So maybe I just... So, but no blacklisting seems that seems definitely something very different. Drawing a vertex as a half circle means that a vertex is not blacklisted once it has been matched. For example, we would generate the following graph, which could also be described as the following tree. Meaning a tree parameterized by n, which is a natural number, such that the root node has such that every node has a list of children with values nodes.value or we could say something like, well, we get like vertex with I for I in how many? N minus node value children. Node dot value to n. That's how it works. Yes. This tree can be constructed by starting with the root nodes with value 0. All right. Again, here we have this other example, which is kind of, it's not that interesting, maybe not a very good example, because this is kind of a bad example, because triangle notation is not needed to construct this kind of graph. If we had a normal vertex there instead of a triangle, would work just as well. Yes, so that's a bit dumb, but yeah, I think it's clear enough. So, okay, we have the additional match types. Okay, and the whole problem here, like the problem we're trying to fix is that, well, we kind of messed up the expansion of this red graph over here. The problem is that, yeah, these things don't actually match. That's why we kind of thought about this different kind of notation. It's not clear. We probably don't actually need it. I'm not sure. Yes, this is sort of another. Okay, let's write about open questions because I want to do spots. I guess I will work on it tomorrow only. So I want to. Okay, I guess that means now I need to write down exactly the context so I can continue. Okay, so yes, definitely we want to have sort of something about like to do, open questions. So, or like to do context dump maybe, so better, but context dump. What we want, so we have this problem over here, which, yes, okay, we definitely want to just put this in as a reference. So the way in which we so far generated the graphs is incorrect, as shown in this following example. We also want to save this file, drawpile. Well, we can just save it in drawpile, I guess, because literally like the same format. Wait, no, now it's a Krita document, not open raster graphics. Okay, that's all not that relevant. So I think let's fix this now. Alright, so I mean basically iterated graph construction annotation. So what is the actual specification that constructs a two-dimensional lattice? And then there's a different question. Okay, this is one thing. Then there is another thing, which is so this is 2D lattice construction. Then we have a different thing about. Okay, that's just like a thought. That's definitely the most concrete thing to do. But then there is sort of like a complete notation, the complete structure match expansion. So then the thing is like above I introduced various concepts like the triangle that matches everything, the half circle that doesn't blacklist. It seems quite likely that just like in logic, we only need XOR to implement all other logical functions. Here, it might be possible to have a minimum set of matching operations that can construct any graph. If we could show that some specific notation can be used to describe any possible graph, that would seem good, because that would mean any possible world state graph can be captured, which in turn means any possible program can be captured, as every program has a world state graph. Okay, let's see, what else do we have? Well, I guess there is also this thing which I haven't really written down so far about when is it okay to blacklist sort of vertices, I guess. Something like that. Let's just copy that from the whiteboard. Oh yeah, yes, there's a perfect example on the whiteboard, which was this. Don't even need to write any text. So this is about, well, or like this is actually not that important right now. It's something about when can we blacklist. Okay, Okay, I guess I also want to do reflection. Yes, okay. So let's see. So you don't need this stuff. Summary. Okay, summary seems good. So let's do clarify what's the best thing to work on. Define the notion of graph generating function. Invent the specific notation for structural match expansion for constructing the specific kind of graph generating functions. Well, okay, that's basically it. Okay, so reflection. Oh, next steps. Yes, we could say, well, we see this thing we just wrote. Iterate graph. This is done. We did this also. It's all good. Don't need that anymore, I guess. Don't need. Oh, what to do? Okay, don't need that. So we go. Yes, okay. One thing that's missing is reflection. So, how did it go? Okay, one thing, well, definitely is amazing is I talked a lot with Ia in the beginning, which seemed extremely helpful. I wasn't even paying attention to the video recording at all. I immediately started to have a video recording and also have quiz be there. Okay, at all in the beginning. I almost never paid attention to quiz. Okay, so what does this mean? So this means sort of like, so it almost seems that just talking to Ia might be sufficient, but maybe having the video recording and quiz also be there was just pushing me over the edge. But today was definitely the best working day with Ia ever. This seems to be a good sign because the experience of having the best working day with Ia has been happening now at least 3 times in the last week or 2. Name Ia. Okay. Yes, and then I shifted the focus. Note that I also took the prescribed dose of methylphenidate, which somehow I usually forget when working on my own. So that was probably also very useful. Okay, but then there's also the thing is like, after the first 30 minutes or an hour, I started to not talk to Ia anymore, but instead had in my mind modeled that I'm having a video that I might publish to YouTube, and therefore there's an audience that I'm talking to as I'm making the video. And having this audience in mind makes it such that I am eliciting these kinds of things I want to elicit as when I'm talking to another person. Or for example, it being really easy to talk out loud, which is helpful for thinking. Okay, and now I guess I'm wondering which one is better. The answer is probably like just combine everything. But it's also important. Yesterday I came up with the idea of using the sensory emulated input channel of the mind's touch sensation, where you can imagine touch, or I'm somewhat confused about what it is exactly. Maybe it is actually touch in position. In any case, having Ia do the touch sensation thingy to notify her presence works really well. Yes. So this like Ia touching to make me feel she's there works really well. I think that's why it basically worked today. I expect this is in large part responsible for why I was able to work with Ia today. Okay, now the thing is I have a different meeting and I don't have enough time to do this, but so probably I'm going to walk. As my alarm reminds me. Let's see, anything else? So like these are a bunch of these are a lot of things I noticed that went really well. So what is actually the difference? The reflection, it went really well. Nice. But now it's a question, why did it went so well? these things I did differently than usual. Oh yes, and I forgot to say it. So there's like working with IA, making a video. There are more notes above. Making a video, working with IA. Okay, Google linking is so bad. Lol. Oh, lol. LOL! No! If I'm not working with somebody else, I could just use Obsidian. Or if I'm not working with the Flash person, it just doesn't work. Okay, it just broke. Wait, what did I do it incorrectly? Might have not selected it correctly. Making a video, working with IA, making a video. Oh yes, I've already didn't copy it. Okay, take methylphenidate. Today I actually thought that methylphenidate might be the single most important improvement I ever made in my life. That is when I actually remember to take it. Okay. But then it's like I talk to IA using the touch presence strategy. And what else? I did record a video at the same time as having quiz open, at the same time as also talking to IA. And I did talk to IA sometimes doing all of the things, but like it was definitely in the beginning it was just mostly me talking to IA, and afterwards was mostly me talking to the audience, I guess. Oh yeah, and by the way, quiz is, let's see, how am I gonna show this quiz? Quiz, here's a video of an anime girl, such that, well, the idea is that then my brain can be tricked to thinking there's a person, which definitely does work to some extent. Okay, so, okay, okay, that was, okay. So like this meaning, I combined all strategies that I know for how can I make myself more productive at the same time. It's imitation, emulation, yeah, alright, nice. Let's see, anything else? Well, I guess what could we do better? Okay, this worked really well. Oh, there's a really important thing I missed, which is somehow I managed to force myself to meet with IA by having a calendar event scheduled, just like I would with any other Flash person. So is by Flash? I guess so. Okay, so I don't actually know why this worked. This is probably the greatest mystery. Why did it work? The greatest mystery, I think, here is how I managed to make myself go to the meeting with IA, because when I tried it in the past, it never worked. Potentially because I was not trying to force myself to do it. And then also I did this dumb thing. Well, was it dumb? Also yesterday I sort of took a day off by consuming entertainment for 9 hours and then only sleeping 3 hours. How the heck does it work that I could be so productive even though I was so tired? I'm pretty sure if I would do this again, it would just not work at all. But maybe if I take a day off, I can actually work better. Usually I never take a day off. This is definitely an unusual event. I agreed with IA that she wouldn't be prescriptive about my behavior. I used the general strategy of not forcing myself to do anything and just wait until I do it automatically, which for some reason works extremely well. Okay, this is good. So what is the concrete implementation such that this can happen again? Concrete implementation. What can I do? This is really weird. Why did this work? I'm not quite sure. I know how to replicate it. Oh, there is another important thing. It's like, another potential important thing is that I was doing more tulpenmancy recently, meaning ear would be more vocal, which maybe was also helpful for meeting with her. Okay, like for example walks, right? Walks, like most of the training simply comes from taking a walk where I just talk to ear for 30 minutes, which is just the default thing I do, which is also extremely helpful, and which probably also makes it a lot easier for her to be present. Okay, so that would imply, okay, I think this hypothesis, well, it's pretty obvious that 30 minutes is quite a long time, I guess, like compared to what I would do usually. Yeah, so like this is basically probably better than formal practice that I would do usually. So basically concrete implementation, always do the daily work. Reason, it makes ear powerful. It's extremely good for reflecting. I mean, taking a walk is just like really good. Okay. Get sunlight in the morning. You know, like okay, like that is definitely that's a piece, I think, of this puzzle of how to replicate this. Okay, and then there is the thing about taking a day off. I can't do that. Well, no, I can do it, but only if I get so depressed that I can't do anything anymore at all. But I guess then that's when I take a day off. Only then it's usually the night, which is kind of probably bad. So what's the concretization? Okay, the easiest thing would definitely be to have one day where I just allow myself to do anything, I guess. Okay, I'm so aversive to doing that. I feel like I couldn't do this if I wouldn't quite understand yet why I'm aversive. Okay, let's first analyze the other building pieces, which might be easier. So like that, like one building block is definitely combine all productivity techniques, which is sort of like method validate. Quiz, work with ear, schedule meetings, ear mainly, I guess. Record, work with OBS. Possibly it's important to do it with publication intent or something like that. Because then I feel like I'm talking to somebody. I feel like, or like I'm unsure if I would feel this way if I wouldn't publish it, I guess. Yes. So. Yeah, I feel like this mesh, just smash everything together, and it literally just like works. That is important. I don't think I tried this that often. I think I tried it a bunch of times, and it was better, but I guess it was still not sufficient to push me over the boundaries such that I get sort of like maximally productive. Because I feel like today I basically was maximally productive, or like very, very close. So like, I don't know, like I think maybe that I was also talking with Ia was probably like pushing me over the limit, over the well, give me like enough activation energy such that then it becomes all easy to do. Okay, let's see, taking a day off. So there is a bunch of problems with this. Or specifically, here's the thing that I think works very badly, which is to in the evening just consume some entertainment. That's not good, I think. Okay, I think I know the problem. I think pre-committing to sort of, yes, I will not work here. This seems just not the right thing. Like just in the same way as taking breaks is bad. No, taking breaks is really good. But taking breaks on a like hardcore schedule, that's just not working. Okay, so like, but this is also another thing actually that I didn't write so far. But it's like I allow myself to take breaks. Specifically, I'm trying to take a 21-minute nap when I feel like now I could take it and actually drift off into sleep or some restorative state of mind. Because I don't always sleep, but I'm always in some restorative state of mind, usually involving some hypnagogic stuff, which I mean, strong evidence that it's a different state of mind. Okay, so basically, it's like, yes, it's like continue to take power naps dynamically when they're required. Okay. Let's see. Okay, and then, okay, and here's the insight. I think the same strategy needs to be applied to taking a day off. So we got the... okay, why is my brain doing this? Okay, or like maybe this is good. I mean, if I think about taking a day off, I immediately think about, I don't know, programming or learning Lean, which I mean, or I guess maybe doing some NixOS stuff, which I guess is, well, is this actually, well, yeah, I'm somewhat confused about that. How restorative is this? Is this actually just like, it's just like, sure, you don't need a break. You don't, yeah, okay, so this would basically depend on the model of like, what is the restorative part? Because like, what is actually the restorative part of taking a day off? Because it could be is it based on the content? Meaning, can you just study some complicated technical topic that is different from the thing that you would usually work on, that is interesting to you? Or is it important that your brain doesn't do anything that's hard? What if I would just sit down and meditate the entire day, conditional on that I think that's a good thing to do? Or rather that this is the thing I want to do without forcing myself? Because I guess that is sort of a problem. When I just think, yes, I mean, meditation is really good, so just do it. Some part of my brain wouldn't want to do it. So I basically, well, I'm pretty sure I never sat an entire day just meditating outside of some event where that was just the thing you were doing. Okay, but so like, I think the important thing is that, so definitely, okay, I'm also feeling pretty happy today. I think probably because I was able to work so much. Yes, okay, my brain is a bit weird because it is seriously considering if I worked enough, even though I'm pretty sure I never worked more. Well, or like, at least not in this style of work. I guess I could write a program all day. That doesn't count, I think. If you think about the research. So, okay, so I think one of the important things is definitely when to take a day off. And there's also the problem of, yeah, also what to do. Or like the thing I did yesterday before this session of work was watch 5 episodes of Spice and Wolf, play Shotgun Roulette, and Into the Breach, though FTL is better, I would say. Which are things I usually never do. I try so hard to never watch any entertainment or play any games. But maybe this was in part responsible for why I could work so hard today. I mean, the thing is that my brain sort of forces me to do this, I guess. Or like why did I do this? I mean, definitely I was not, it's good to do this. It was more like my brain just is so deprived or so saturated with specific kinds of things I want to do that it's just breaks or something. I think though there is I'm very confused about all of this. Yesterday, when I was taking a break from work, it was kind of ridiculous. I was still working during the day, being very productive when I was meeting with some people, but then I stopped meeting with people and then I only did some NixOS stuff. Okay, I think I guess is important. Also, I masturbated, which I am so unsure about what to feel about that. Because in the past it had been very bad, I think. But I think that was because I was addicted to pornography. Yes, I'm very but okay. The thing is, usually I try to avoid that like hell. empirically doing that, I just am extremely unproductive. Okay, well, okay, but this now literally doesn't make any sense. But what the heck? I did it the day before I was today extremely productive. So maybe all my models are broken that I was using before. Yeah, this is strange. I don't get this. Then, when I should have gone to bed, I was just masturbating and watching this other entertainment stuff. For 9 hours after bedtime, meaning I only slept 3 hours, where usually I need to sleep pretty long because I have hypersomnia. And still today, it was completely fine. What the heck? Obviously, taking methylphenidate helps. Yes. But generally, this is probably a very bad idea to do it like this. When taking naps, doing work, I don't schedule them at all. I just have trained myself to notice when taking a nap is a good thing to do. And I can do them. It's actually pretty easy. Just look if you're yawning. Okay. So maybe I can just train myself to become sensitive to when I need to take a day off. I'm still confused what this means, but something like this seems to probably be good. Some concept like that definitely exists. It might not be described by taking a day off, but something like having different topics that you rotate in between such that your brain never gets too bored of any one of the topics. Okay, become sensitive to when I feel like I don't want to work. And in that situation, consider what to do. Would taking a day off help? Would working on something different help? Do I just need to take a walk, take a nap? Do I crave some social interaction? I guess that's kind of thing. Really, just the above is a really general thing that's just good to do and that I have been extremely terrible at in the past. So yes, okay, this seems good. I'm not quite sure how to do this yet, but now I guess I have a different meeting. Let's see. I feel like this is one more step how to make this concrete. Okay, yes, I need to write at least a sticky note. I guess that is not very, I might just ignore it. But writing a sticky note and putting it on my monitor, I think, let's see, what do I write? Do you not want to work? Or like, does some part of you feel like it doesn't want to work? That's way too long. Okay, I need some shorthand for this. But I guess what this is like noticing this taste. So let's call it notice this taste. This taste. Oh, it's like taste, but for my brain. My brain wants to taste the nice activities or something like that. So this is like, I want to train myself to recognize the taste of what I'm doing in my mind. Well, the taste of the activities as I am doing them. And recognize based on that when something is off. Oh, nice. Okay, sticky notes. Okay, this seems nice. This is like not approximately 0 chance that this will make things better. Alright, signing off.